Flipped classroom video for Maths AS Unit 1, Quadratic Inequalities. Quadratic inequalities are much trickier than linear ones. Essentially, this is because quadratic equations go down and then up, or vice versa. And so it makes the situation much more complicated. We can solve them algebraically, but it can be easier to use a graphical approach either instead of or in addition to some algebra. We've seen an example of this in a previous video about quadratics, and it was when we had a quadratic inside another quadratic essentially. But in case you haven't seen it, we're going to run through it anyway, slightly differently presented. So what we're looking at is, what are the values of k that mean that k squared minus 4k minus 12 is greater than or equal to or less than 0? And the first thing we do in this situation is we factorize the quadratic. So we have a constant of minus 12, so we need the pairs that multiply to that, 1, 12, 2 and 6, 3 and 4. We also notice that the pair that's going to add up is going to add up to minus 4, so we need the larger numbers to be negative, and then we can identify 2 and minus 6 does the job. So that means that k squared minus 4k minus 12 is equal to k plus 2 times k minus 6. So that tells us that the roots of this quadratic are minus 2 and 6. Okay, the best way to find out which values of k give the various outcomes is to sketch it. And we know we have a cup-shaped graph because the coefficient of k squared is positive, and so we can start by drawing the curve itself. Then we put the x-axis on with the roots of minus 2 and 6, and then we can say that part is greater than 0, so we need those two bits, and that means we're looking at k being less than minus 2 or greater than 6, and for those values the original quadratic k squared minus 4k minus 12 is greater than 0. Then we have the equals 0 of course, so we can say that when k equals minus 2 or k equals 6, k squared minus 4k minus 12 is equal to 0. And then below 0 we have this portion here, and so we say that when k is between minus 2 and 6, then k squared minus 4k minus 12 is less than 0. And if we wanted to check this, we can try various values of k in the original quadratic to make sure. So we might try 0. If we put 0 into k squared minus 4k minus 12, we get minus 12, and according to our purple inequality, 0 is between minus 2 and 6, and therefore it should be less than 0. So that's a bit of confirmation, and we could check one or two other answers if we wished. We can solve quadratic inequalities algebraically, but we need to take care. It's easy to miss out possible cases or to get things the wrong way round. So let's have a look at an example. This is an example of a quadratic which factorizes. So we have x squared plus 3x minus 4, and we can see that if we use 4 and minus 1, they multiply to minus 4 and they add up to 3, so that's our factorization. And then we're going to look at this one first. We're going to look at, because we have two things multiplied together that are positive or greater than 0, that means we either have them both greater than 0 or both less than 0. Well, we're going to look at the both less than 0 first, and I would mention that this is one of the common errors, is that when students have a go at these, they forget this case of them both being less than 0 and just look at them both being greater than 0, so that's one of the risks of doing it algebraically. Anyway, we'll carry on with this. So the first one, x plus 4 being less than 0, tells us that x is less than minus 4, and the second one tells us that x is less than 1. Now, this is another place where it's easy to get things wrong, but we'll just have a quick look at this with a number line. The first one tells us that we're looking at values from minus 4 downwards. The second one tells us that we're looking from values from 1 downwards. Now, we need both of these to be true. This is not an or, this is an and. They both need to be true. So that means the actual one that we need is x is less than minus 4. Okay, we'll now look at the case of both brackets being positive. So that means x is greater than minus 4 and x is greater than 1. And in this case, for them both to be true, we need x to be greater than 1. Graphically, this looks like this, and this is perhaps why I personally think the graphical method is quite good, safer than the algebraic method, is that if we just draw ourselves a curve, pop in the roots, we can then say we want the bits above the line, so that's those two bits, and sure enough, that gives us our answers. In interval form, we'd say x is a member of minus infinity up to minus 4, or between 1 and infinity. And we can see that the right hand side of the quadratic sketch is represented by x is greater than 1, and the left hand side by x is less than minus 4. So that just links the graphical method with the strictly algebraic method. Now we'll look at an example that doesn't factorize, and there's different ways of doing this, but one rather neat way is to use completing the square. What we would do is we'd add 7 to both sides, so that we have x squared minus 4x is less than or equal to 7. We'd then complete the square on the left hand side, so we have x minus 2 squared, take away minus 2 squared is less than or equal to 7. The minus 2 squared is of course 4, so we have minus 4 there, so by adding it to both sides we end up with x minus 2 squared is less than or equal to 7 plus 4, which means it's less than or equal to 11. Now, what that tells us is that x minus 2 must lie between root 11 and minus root 11. If we think about the square being less than or equal to 11, then any number in that range I've given, when you square it, has to be less than 11. If we go beyond root 11 in the positive direction, then anything bigger than that is going to square to more than 11. But that's true also if we go beyond minus root 11 in the negative direction. And so this is why completing the square works rather nicely here, because it gives us our answer pretty much straight away. What we can do to finish this off is we can add 2 to each of the bits there, so that will give us 2 minus root 11 is less than or equal to x, which is less than or equal to 2 plus root 11. Okay, graphically we would draw ourselves a curve. Now the roots, we can actually get them by considering what I've just said. We'd have to do a bit more writing to show it, but we can see, hopefully you can see that those are the roots in this situation. And then we know that we need below the y equals 0 line, and so we get the same result as before, of course. X is a member of the interval from 2 minus root 11 up to 2 plus root 11, square brackets both ends because both boundaries are included. And just to reiterate, that squiggly bit that I've shaded is indeed the same as the algebraic answer. You may also come across modelling with quadratic inequalities in some sort of real life type situation. This example is that we have a projectile, so something's being chucked in the air, and its vertical displacement, so how high it is in other words, is given by y equals 12t minus 5t squared, and in this situation y is the height and t is the time from launching. So the question is, for how long is the projectile above a height of 4 meters? Whether we care or not, we have to find out. So what do we need to do? Well, what we're saying is that the height which is represented by 12t minus 5t squared needs to be greater than 4. And so we can solve this. And notice the first thing I've done here is I've times through by minus 1. Now that's because I want the 5t squared to be positive, but by timesing through by minus 1. That's fine with 12t becoming minus 12t and 4 becoming minus 4, but we must remember also to swap round the direction of the inequality because we're timesing by a negative. Okay, once we've done that, divide through by 5, so I've got t squared on its own. Then we can complete the square, so half of 12 over 5 is 6 over 5. So that gives us t minus 6 over 5 squared, take away minus 6 over 5 squared, is less than minus 4 over 5. And that gives us the next line. Well, minus 6 over 5 is squared is 36 over 25, so that was subtracted on the left hand side, so when we add it on to both sides we get this. T minus 6 over 5 squared is less than minus 4 over 5 plus 36 over 25. By recognising that 4 over 5 is 20 over 25, that gives us minus 20 over 25 plus 36 over 25, which is 16 over 25, which is rather convenient because both of those are square numbers. And we can square root and pop the t minus 6 over 5 in the middle there, and this is the same argument as before, that if t minus 6 over 5 squared is less than 16 over 25, then it must lie between minus 4 over 5 and plus 4 over 5, which is the square root of 16 over 25. Next we can add 6 over 5 to both sides, or all bits rather, both the left and the right hand sides and the middle, and we get minus 4 over 5 plus 6 over 5 is less than t, which is less than 4 over 5 plus 6 over 5. That gives us t lies between 2 over 5 and 2. They are strict inequalities because we want to know for how long it's above a height of 4 meters. That's the graph that shows this situation. That isn't the projectile travelling along, it's just showing what height it's at a particular time, and we can see that our 0.4 and our 2 is correct. And so finally we can say how long the particle was above, or the projectile rather, was above a height of 4 meters, and that was between 2/5 and 2 seconds, and so t is equal to 2 take away 2/5, which is 8/5, which is 1.6 seconds.